Everybody?
Yes.
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 Okay. And the screen is also visible.
Yes.
Okay.
Yes, sir.
Okay, let's begin. And there has been some time which has elapsed after our last lecture. Of course, we had a great talk on meta learning. Now we'll continue with probability and statistics for AI. So today is lecture 8. And let us be somewhat rigorous and technical about our claims. The foundation for a lot of things in dealing with data and making a systematic approach to use of data for useful purposes. That is called data science. Okay, and it is somewhat amusing to mathematicians and statisticians that what they have been doing for decades is now called data science, analytics, and so on. But there is a huge body of knowledge, an extremely elegant, high-level knowledge, which has been developed in mathematics and statistics, and which are being found useful in dealing with data today. And data, as we all know, forms the oil for new age AI. Everything we do now can benefit from data. At the same time, we also, this is my favorite statement, that if you do not have data, you will have to peek into your mind, into the brain. So if I do not have data, I have to think. So absence of data actually forces us to understand a problem, understand mathematical structures, physical phenomena, chemical phenomena, biological phenomena, material science phenomena, much more closely. We really have to think on the phenomena. So thinking and data are complementary to each other, but too much of emphasis on data should not reduce our brain power. We should not lose sight of the phenomenon, and at the same time, overemphasis on hypothesis formation, creating assumptions based on our thinking, which is not based on reality, should be avoided, and that is where data comes into the picture and helps us. So data and thinking both have to go hand in hand. So now this is the lectures that we are taking now, and the discourse that we are doing is an example of human mind at its best. Okay, human intellect at its pinnacle, absolute pinnacle. So one of them is central limit theorem, which is the basis of a lot of statistics, and if you want to use a popular term, data science. So we want to look at the rigorous steps for central limit theorem, proceed to interval estimate, and take firm steps towards hypothesis testing. Now, central limit theorem has been mentioned so many times. The statement also has been given many times. So we again go to the central limit theorem. If you have seen this before, it is okay. There has been some gap between today's lecture and the last discussion on central limit theorem. So personally, I find it very intriguing that the sum of n random variables, when n is sufficiently large, also follows a normal distribution. Not also, follows a normal distribution, independent of the underlying distribution that each of these random variables have. The only constraint is that all these random variables must have mean mu and variance sigma square, same mean and same variance. And that constraint is satisfied if we are drawing a sample from a population. For example, if I denote the first draw, second draw, third draw as different random variables, and they have their independent existence. This is with replacement or from an infinite population. Then this sum follows a normal distribution, okay, if n is sufficiently large. And that n being sufficiently large is also dropped if each of these random variables is normally distributed. Okay, so the sum of n random variables follows a normal distribution for n sufficiently large. That, I think, is an extremely intriguing fact. And if it is normally distributed, then its mu mean is n mu, sum of the means, and the variance is the sum of variances, so that the standard deviation for this sum is sigma root n, because n sigma square is the variance. It is the standard deviation is sigma root n. In the last lecture, I think we proved that the mean of sum of n random variables, each with mean mu, is n mu, and the variance of the sum is n into variance of each of these random variables. So variances sum, means also add up, but they preserve the sign. Means preserve the sign, variances just add up. That was proved last time, if you recall. So if Sn, which is the sum of these n random variables, is normally distributed with mean n mu and variance n sigma square, then we can say that Sn minus n mu divided by sigma root n, that is Sn minus mean divided by standard deviation, is a standard normal variable. So if I can prove this, I have also proved the fact that sum of these n random variables is normally distributed with n mu and n sigma square as mean and variance respectively. So now the onus is on us to prove that Sn minus n mu divided by sigma root n is a standard normal variable. Okay, and that itself is a very intriguing fact. Now, by a little bit of mathematical adjustment, I can also write Sn star as equal to Sn minus mu divided by sigma by root n. So I can divide by n both the numerator and the denominator, and Sn by n minus mu by sigma root n by n, which is equal to x bar minus mu divided by sigma by root n, is a standard normal variable. Okay, so the purpose behind this adjustment is this. This is this gives rise to an equivalent statement of central limit theorem. This says that x1, x2, x3, xn be n independent random variables forming a sample from a population with mean mu and variance sigma square. Then the sample mean is normally distributed with mean mu and variance sigma square by n. Okay, so this is an equivalent statement of central limit theorem. So central limit theorem is stated either as sum of random variables or the mean of the sample. Okay, sum of random variables, these random variables form a sample. Okay, so we have two equivalent statements of central limit theorem. Sum of random variables is normally distributed, or equivalently, the sample mean is normally distributed. Okay, so both the statements are equivalent, and their use is seen in different problem situations. Now let's proceed to the proof, and I would like to tell you, since we are in the age of data science, that all these knowledge that has been gathered over centuries, some of them made use of data, and some were absolute strokes of genius because they understood the phenomenon and the constraints and laws underlying a phenomenon. So here I'm tempted to tell you a small story, which is which concerns Kepler and Tycho Brahe. So a lot of laws in physical sciences are obtained from data, as well as from the tremendous insight that human beings have into the processes of creation. So Kepler gave these laws of planetary motion. One of the most remarkable statements, there are three laws of planetary motion due to Kepler. One of them says that the area traversed is inversely proportional to the distance. So the planets have an elliptical trajectory around the sun. Okay, and the sun stays in one of the foci of this elliptical path. So these laws were arrived at by Kepler, and the story goes that he did this by processing the enormous amount of data that Tycho Brahe collected over many years by painfully observing the motion of the planets. So Tycho Brahe was not ready to part with the data. He was not willing to give it to anybody, but Kepler stole it, analyzed the data, had this tremendous insight into planetary motion, and they are distilled into these three laws of planetary motion due to Kepler. So this is an example of data science helping uncover laws of nature. But there are also many examples where data did not really lead to the law or understanding of the rule, but it was leap of generalization by human mind. So the point I'm making is thinking and data both have to go hand in hand. Now, one of the great examples of very creative thinking is this central limit theorem, now the moment generating function, which statisticians, mathematicians have devised for dealing with mathematical theorems, statistical theorems, and phenomena. Moment generating function is defined for a random variable x. For a random variable x, the moment generating function mxt, t is an introduced variable, is expectation of e to the power tx. Expectation of e to the power tx. Now, in mathematics, it is often very useful to think about why somebody thinks of a formula. That motivation behind that formulation Einstein calls it as third part understanding. Okay. The first part understanding is you know a fact. Okay. The second part understanding is you know how to use that fact. And third part understanding is why that fact. Okay. First what, then how, and then why. So Einstein used to say that our understanding is incomplete until we have gone up to the third stage of understanding. What, how, and why. So moment generating function, why somebody would think about that is very instructive to know. And actually, this is conceived to set up a platform from which all the moments are generated. So mean is the first moment, standard deviation is the second moment, kurtosis is the third moment, skewness is the fourth moment. So all these are measured with respect to the mean and raising the difference of the value of the variable from the mean to a power. Okay, so the standard deviation is expectation of x minus mu square. Okay, so that's how you get the second moment or the standard deviation. So e to the power tx actually generates different moments, mean, standard deviation, and so on. And how one would think of an exponential function to do this job of generating moments is, to my mind, extremely creative and stroke of genius. So anyway, proceeding with the mathematical formulation, the moment generating function of a random variable x with the introduction of the controlling variable t is expectation of e to the power tx. Now, if x is following a discrete distribution, let's say x takes n variables, n values. For example, the throw of dice takes 6 values. So j equal to 1 to n sigma e to the power txj fxj, where fxj is the probability mass function. Fxj associates a probability with each value xj. Okay, so I associate a probability with the outcome of 3 when 3 is where 3 is produced by the throw of the dice. So can somebody verify that you are seeing moment generating function slide?
Yes, sir.
Okay, great. So fxj is the probability mass function giving a probability value to each value of the random variable xj. So the moment generating function by definition would be the expectation of e to the power tx, which is value into probability. So e to the power txj is the value of this random variable, and the probability is the probability of xj. When I come to continuous distribution, then e to the power tx is the value. Now PMF will not do. I need PDF, probability density function. So fx dx, fx is the probability density function, dx, and integrate from minus infinity to plus infinity, you get the expectation of e to the power tx, which is equivalent to the moment generating function for the random variable x. Proceeding further, this is another very important theorem in statistics. Again, we will not have any hesitation in calling it one of the pinnacles and human intellect, the uniqueness theorem. Suppose x and y are random variables having moment generating functions mxt and myt respectively. then X and Y have the same probability distribution if and only if mxt equal to myt identically. So there is one-to-one correspondence between a random variable and its moment generating function in the sense of the equivalence or equality or identicalness of distributions. So if I take two random variables x and y, and if I can show that their moment generating functions are identical, then their underlying distribution also must be identical. So this is the uniqueness theorem, and it is also vice versa. Okay. So to appreciate the power of this theorem, the uniqueness theorem, let's look at the task on hand, namely proving the central limit theorem. So we have decided on this agenda that we want to prove the central limit theorem, namely n random variables, their sum is normally distributed with mean n mu and variance n sigma square. This will be proved if we can prove that the corresponding standardized variable. What is the meaning of standardization of variable? You subtract the mean, divide by standard deviation. So Sn minus n mu divided by sigma root n. This standardized variable is normally distributed. If we can show that, then we are done. Now for that, we'll appeal to the uniqueness theorem. We'll show that Sn minus n mu divided by n divided by sigma root n is a standard normal variable. Okay, and all standard normal variables have mean as 0, standard deviation as 1. So the standard normal variable, standard normal distribution has this form: probability that the random variable takes the value y is equal to 1 by root 2 pi e to the power minus y square by 2. So this is y minus 0, 0 is mean, and this is root 2 pi sigma, sigma is equal to 1. So standard normal distributions probability density function is 1 by root 2 pi e to the power minus y square by 2. Let's see what would be the moment generating function of standard normal variable. Okay, so the MGF by definition would be e to the power ty, okay, e to the power ty 1 by root 2 pi e to the power minus y square by 2 dy. So the value of the random variable e to the power ty and the probability density function 1 by root 2 pi e to the power minus y square by 2 and dy. So now I can take this ty inside this bracket. Both are e to the power 2 pi, e to the power some quantity. Now I can add these, so it is e to the power minus y square by 2 plus dy. So it is of the form a square plus or minus 2ab. I need to introduce a b square. So I take this minus outside, take this half also outside. So I get y square minus 2yt. And if I add t square, I have the form a square minus 2ab plus b square. But since I have added t square by 2, that is minus t square by 2, I have to compensate by multiplying by e to the power t square by 2. So now 1 by root 2 pi can go out of the integration. No, I need not. I will not. 1 by root 2 pi stays, but e to the power t square by 2 is independent of y. So I take it outside the integration sign. Now I have minus infinity to plus infinity 1 by root 2 pi e to the power minus half y minus t square dy. Okay, so this algebra is fine, following step by step. Now this integration might seem like a complicated task to resolve, but not really so, because 1 by root 2 pi into e to the power minus half y minus t square is actually a normal distribution, is an expression of a normal distribution where the sigma or the standard deviation is 1 and the mean is t. And this integration minus infinity to plus infinity is nothing but the area under a normally distributed random variables curve or probability distribution. Okay, so this is the area under the normal curve where the normal distribution has standard deviation was 1 and mean t. So the area must be equal to 1 by definition of probability distribution. So the moment generating function for standard normal distribution is e to the power t square by 2, where t is the controlling variable. So I have finished half my job. I have found out the MGF of standard normal distribution. Now if I can show that the MGF of the Sn, which is sum of n random variables, each has mean mu and variance sigma square, if the moment generating function of that also, as n becomes larger and larger, is e to the power t square by 2, then I am done. Okay, so Sn minus n mu by sigma root n. If the moment generating function of this quantity is also e to the power t square by 2, then I have proved my theorem. Okay, so let's proceed. So to prove that Sn star equal to Sn minus n mu divided by sigma root n is a standard normal variable, I am interested in knowing what the form of moment generating function for Sn star is. So moment generating function for Sn star is m Sn star lower suffix t. T is the controlling variable. And Sn star is supposed to be a standard normal variable. So I need to show that this is mzt. Z is standard normal variable. You remember the Z score table, which we have applied many times for many problems. Now let us see what the moment generating function of Sn star is. I have to do these mathematical operations. I have to multiply Sn star by t and raise it to the power of e, and then take its expectation. So e to the power t Sn star and expectation thereof is equal to expectation of e to the power expansion of Sn star. Expansion of Sn star is t into Sn minus n mu divided by sigma root n. That is the expression for Sn star. Now, each random variable x1, x2 up to xn has same mean mu and same standard deviation sigma square. They are identically distributed with same mean and same sigma. So this I can write as t, and Sn is nothing but I equal to 1 to n sigma xi minus n mu divided by sigma root n. So Sn is equal to sigma xi I equal to 1 to n. Now I can take this n, I can take this t inside, and I equal to 1 to n sigma goes outside. So this is Txi minus mu divided by sigma root n. So n mu is sigma I equal to 1 to n mu. Mu is a constant. So I can take this whole sigma outside and bring t inside. So I get Txi minus mu divided by sigma root n I equal to 1 to n. Now e to the power a plus b is e to the power a into e to the power b. So therefore this sigma can now come down as a product I equal to 1 to n e to the power Txi minus mu divided by sigma root n, the product of all these e to the power Txi minus mu divided by sigma root n. Now expectation of product of random variables, independent random variables, is product of expectation of these random variables. So this E can move inside. We can very easily prove it from the definition of expectation, but you might want to justify to yourself that E can move inside. Yes, we are making use of the fact that expectation of product is product of expectation provided the random variables are independent of each other, which is the case for the discussion going on now. Now we have an interesting situation, product of expectations of identically distributed random variables. So I can absorb this product or remove this product by raising the inside quantity to the power n. Okay, so this is actually a into a into a n times, and these xi's are all identical. Okay, identically distributed. So that's why this raising to the power is all right. So if you have any doubt about that, we can discuss this later, or you yourself can verify this later. So this is a key step that eliminates the product and raises everything to the power of n. Let's proceed further. Now we have arrived at this particular step. Expectation of e to the power t into xi minus mu divided by sigma root n to the power raised to the power n. And now we would like to examine the quantity e to the power Txi minus mu divided by sigma root n. This is a quantity e to the power some capital M, let's say. Okay, and we know from Taylor series expansion or expansion of e to the power x that this is 1 plus x by factorial 1 plus x squared by factorial 2 plus x cubed by factorial 3 and so on. So here my exponent is t into xi minus mu divided by sigma root n. That is the exponent. And Taylor series allows me to write this as 1 plus exponent by factorial 1 plus exponent by factorial 2 plus exponent cube by factorial 3 and so on. So this is a major step in the derivation. Now I have expectation of these series now. So proceeding further, we work with E. Now this is expectation of 1 plus Txi minus mu sigma root n plus t square xi minus mu square by sigma square n and so on. Okay, this came from the definition of the Taylor series expansion. So now expectation can move inside, expectation distributes over addition. So this is expectation of 1 plus t into expectation of xi minus mu. Why so? Because expectation can also move inside a constant into variable. So t sigma root n will come out and expectation will sit over xi minus mu. Expectation of a into x is a into expectation of x. Similarly, t square by 2 sigma square n will come out and E will sit over xi minus mu square and so on. Now expectation of a constant is constant itself. Expectation of xi minus mu is 0. Okay, expectation of xi minus mu is 0 because this is expectation of xi minus expectation of mu. Mu is a constant, expectation of mu is mu, expectation of xi is mu. Mu and mu cancel, so this is 0. Now this is t square by n. Expectation of xi minus mu square by definition is variance. So this is sigma square. So sigma square and sigma square cancel and I get t square by 2n. And then we have subsequent terms with higher powers. So where are we now? We have come to this state that as n tends to infinity, we have to now examine the behavior of expectation of e to the power t Sn star, the moment generating function, which we have deduced by various mathematical steps, is equal to 1 plus t square by 2n plus other terms involving n in the denominator with higher power as n tends to, and to the everything raised to the power n. Now the theorem, central limit theorem, says that as n tends to infinity, Sn becomes normally distributed. Okay, so we have to examine the behavior as n tends to infinity. So can you please verify you're looking at as n tends to infinity?
Yes.
And somebody, okay,
Yes,
fine.
sir.
Yeah. So now I would like to examine the behavior of this quantity 1 plus t square by 2n plus etc. to the power n. I again resort to algebraic manipulations. So I want to study ln equal to 1 plus t square by 2n plus other term raised to the power n. Now ln is equal to 1 plus t square by 2n plus other terms to the power n. I take log on both sides. Then log of ln is equal to n into log of 1 plus t square by 2n plus other terms. Now this is equal to log of 1 plus t square by 2n plus other terms divided by 1 by n. I take n to the denominator and invert it. So this is 1 by n. Now this quantity is what we have arrived at after taking logarithm. So all these are mathematical steps, and do not misunderstand me. In the age of data science, okay, we should not lose sight of these mathematical abilities, composition abilities, okay, analytical abilities into phenomena. Okay, we should not be ruled by data, thinking that all these elegant steps are not necessary. So this step of taking n, which multiplies the log operation, taking it into the denominator in the form of 1 by n, is an essential step in the derivation. Okay, and this is necessary. It shows the power of analysis and ability of mathematical thinking. So we proceed. Now we want to understand the behavior of this quantity as n tends to infinity. Now we make use of another important step in calculus. Another important step in calculus, limit continuity, many centuries old, and that is L'Hopital rule. Okay, we sometimes pronounce this as L'Hospital rule. But actually, this is L'Hospital was a French mathematician, and this is pronounced as L'Hopital rule. So now I take the derivative of the numerator and the denominator. The derivative of the denominator is minus 1 by n square. Okay, minus 1 by n square. The denominator was 1 by n. And the numerator was log of this quantity, which is 1 plus t square by 2n plus other terms. Now log of x, the derivative is 1 by x. So that's why I have 1 by 1 plus t square by 2n plus other terms into derivative of x. Now the derivative of x is 1 derivative is 0, t square by 2n derivative is minus t square by 2n square, and derivative of other terms where n will have higher power and in the denominator. Okay, so this is what, yeah, there's some question? No. Okay, so by L'Hopital rule, I've taken derivative of numerator and denominator and I have arrived at this form. Now something convenient happens to us. This 1 by n square cancels with 1 by n square here, minus t square by 2n square. And that leaves me with t square by 2 divided by 1 plus t square by 2n plus other terms. Now as n tends to infinity, nothing happens to t square by 2, and the denominator tends to 1 because all other terms have division by n or higher power of n. So this becomes 1. So t square by 2 divided by 1, which is t square by 2. So these mathematical operations allow me to reach at this state that the log ln as n tends to infinity, the limit of log ln as n tends to infinity is t square by 2. Okay, and that means that limit of ln as n tends to infinity is e to the power t square by 2. Okay, and what is e to the power t square by 2? It turns out to be the value of expectation of e to the power t Sn star as n tends to infinity. So expectation of e to the power t Sn star as n tends to infinity is e to the power t square by 2. That means the moment generating function for Sn star is e to the power t square by 2. Okay, and what did we see before? We saw that the standard normal variable whose mean is 0 and standard deviation is 1 has also moment generating function as e to the power t square by 2. So the moment generating function of Sn star is e to the power t square by 2. Therefore, Sn star must be a standard normal variable with mean 0 and standard deviation 1. Okay, the fact that mean is 0 and standard deviation is 1 was taken care of by standardization operation when I made Sn minus n mu divided by sigma root n. That made the mean as 0 and standard deviation as 1. What remained to be proved was that this quantity is normally distributed. Okay, the fact that it is normally distributed has been established now by the mediation of the moment generating function. So we have taken a very solid step. Okay, we are on very firm ground due to this statistical mathematical operation and the contribution to knowledge from mathematics and statistics, that the sum of random variables is normally distributed. Okay, and an equivalent statement that the sample mean is normally distributed with mean as mu, standard deviation is sigma by root n. Okay, both the statements are equivalent. So this is a very nice proof, and it gives us a lot of confidence in this phenomenon that I take n random variables all with mean mu and sigma square as variance. Their sum has to be normally distributed. The proof is very nice and beautiful. Okay, so central limit theorem is done. And are there any comments, questions from anybody at this stage?
Yes, sir. So we central limit theorem's definition mainly talks about random variables which are identical or have same
Hmm.
sigma square and same mu, right? So
Yes.
can it be generalized to any random variables where I think we discussed this last time or briefly mentioned it, that it could be mu1, mu2 up to mu n and sigma 1, sigma 2 up to sigma n, and eventually the sum will be distributed with the mean sigma of all mu1, mu i's, and sum of all the variances. That doesn't it?
No, the mean and standard deviation have to be identical, but their
Okay, okay.
distributions need not be normal. Okay,
Oh,
their
okay.
distributions need not be normal. Now, this restriction that all of them must have same mean and same sigma square.
Mm-hmm.
Um, the, is it an artificial constraint? It is not an artificial constraint when we think of sampling situations. We are drawing samples from a population. Okay,
Right,
what to
right, right.
do? What to do when these random variables do not have identical mean and uh, s-
Variance.
uh, identical variance? Then what to do? We'll have to see later. Hmm?
Okay, okay, okay.
Yeah. Anything else? Okay. So let's proceed. Now we come to another very interesting and important discussion, which is interval estimate. Now, this is also very useful to us. Sample mean and population mean. So suppose I'm drawing a sample of size n through random variables x1, x2, x3 up to xn, where x1, x2, x3 up to xn are draws, random variables representing draws, uh, which lead to a sample from the mean. The maximum likelihood point estimator of mu is x bar. So given the sample values, I can compute the sample mean as sigma xi by n. Now, notice that statement carefully and try to prove that the maximum likelihood point estimator of mu is really sigma xi by n. There is a population which I am not able to see. I am only able to study that population. One of the important properties of any population is its mean. So I'm allowed to study this population only through sampling. Okay, it is not practical to look at the whole population. You remember we discussed the problem of sand coming from mining operations. Okay, the sand particles are useful for paint industry, but we're interested in their mean size. Now the mean size of the whole pile of sand is not practically measurable. We only draw a sample from this whole sand pile, and the mean is sigma xi by n. Now try to prove that the maximum likelihood point estimator of mu is this x bar. Okay, this very simple operation of summing up the values and dividing them by n, dividing that sum by n. That is the maximum likelihood point estimator of mu. Just think about this. Okay, this is the best possible estimate of mu given the information at our disposal. The only information I have is the sample value. Okay, the quantity of the value of each quantity as they are drawn from a sample. The only thing I have is that I have the measurement of each sand particle for, let's say, 100 sand particles. That's all I have. And I take the sum, divide by n, and that is the maximum likelihood point estimator of mu. Okay, so try to prove that this indeed is the case. That is a very instructive exercise in probability and statistics. Okay, just reflect on this point for 1 or 2 seconds, that I have a population mean And the maximum likelihood point estimator of that population mean is this quantity. The sum of these variables divided by n, or sample mean.
Okay, so can we start by start with the fact that we know central limit theorem holds and use that to come to this conclusion.
Achha, really? I didn't think of that. How will you do that?
So basically, we know that for all the samples that we are going to draw, so we have some estimate about, or some so we know that each of them is identical first of all, and their sum will have a distribution which is normally distributed with n mu and sigma by root n. So so that is known. So that's why we know the estimate for the sum, no, not estimate, the distribution for this sum, and that's why expectation for the sum divided by n will be expectation of that random variables. So some expectation for this sum divided by n. So I'm not able to visualize everything in my mind, but I
Right,
think
right.
yeah, on paper, can we go this way and try to prove this?
Yeah. So I think your starting point is right. You are just taking the expectation of the right hand side of this quantity.
Right,
Expectation, and then 1 by n will come out as constant, and then you will study the expectation of this summation, and expectation of each of these. Expectation of the sum is sum of expectations, and this
right,
will be the expectation of x1 plus expectation of x2, etc., etc. And then each of these expectation is mu.
right,
So this will be n mu divided by n. Therefore, this is mu. So
right,
expected value of x bar is really equal to mu.
right.
Okay, that's very good. Okay, now the only question is why this term maximum likelihood? Maximum likelihood. So if I take expectation of x bar and expectation of the right hand side, I come to expectation of x bar as equal to mu.
Right.
But what is this point about maximum likelihood? So let's go a little further and take this up. Now, we know that x bar is normally distributed with mean mu and known standard deviation sigma by root n. We know this from central limit theorem. Okay. So the following also is a standard normal distribution. X bar minus mu divided by sigma by root n. So sigma by root n is the sample standard deviation, and sample mean is x bar. So x bar minus mu divided by sigma by root n is also a standard normal variable with mean 0 and standard deviation 1 as per central limit theorem. Now, we are very interested in 95% confidence interval. Okay, that is quite useful to us in many applications. So now I know that since x bar minus mu by sigma by root n is actually z, then from the z-score table I know that probability of minus 1.96 less than z less than 1 plus 1.96 plus, that probability is 0.95. So from minus 1.96 to plus 1.96, the area under the standard normal curve is 0.95, which has been of great use to us in many applications. Now I do a little bit of algebra, and I multiplied by sigma by root n, and I come to this step. Probability of minus 1.96 sigma by root n is less than x bar minus mu is less than 1.96 sigma by root n. That is 0.95. Now from this I come to this step that mu x bar minus 1.96 sigma by root n less than mu less than x bar plus 1.96 sigma by root n. That probability is 0.95. So this is actually a very important observation or conclusion. This is a tremendous step, that the population mean has to lie between x bar minus 1.96 sigma by root n and x bar plus 1.96 sigma by root n. Okay, so I have drawn the sample, I have computed x bar, and from that x bar, and suppose I know the sigma somehow, the standard deviation of the population. I know root n because n is the size of the sample. So this is a tremendous insight that the population mean has to lie between x bar minus 1.96 sigma by root n and x bar plus 1 plus 96 sigma by root n, and the probability that this will happen is as high as 0.95. Okay, so this is a tremendous statement actually, that the population mean must be will lie within this interval with high probability. High probability is 0.95 for us. And see how we arrived at this conclusion by very simple steps. Just made use of the fact that x bar minus mu by sigma by root n is actually z. Then consulted the z-score table, and we know that minus 1.96 to 1.96, that interval probability is 0.95. And then after that, there is simple algebraic manipulation. And I am led to the conclusion that population mean must be within this interval with probability 0.95. And if I want to have higher probability, 0.99 for example, then we know we have to sharpen this limit, minus 1.96 to 1.96, okay, or expand that limit. And this is the conclusion. Now, what is the application of this? So let's take an NLP situation to see the application of this interval estimate. So what we are doing is interval estimate of the population mean based on sample mean. Interval estimate of the population mean based on sample mean. What is the most likely interval in which the population mean will lie? Okay, and what is the probability of lying in that interval? This is the question we are answering, and we are able to answer that question based on sample mean, sample size, and somehow known the standard deviation of the population. Who assisted us in this conclusion? Central limit theorem. Which form of central limit theorem? The sample mean form of central limit theorem. Now, an NLP situation. Suppose that a Hindi Konkani machine translation system called Bhattacharyya has been made, and it is tested as follows. It is tested on 9 test corpora. The blue scores on this test corpora are 5, 8.5, 12, 15, 7, 9, 7.5, 6.5, and 10.5. So the values oscillate, okay, and this is my sample blue score based on 9 test corpus. And suppose somehow it is known that if the machine translation system could be tested on the whole population sample by sample, then the variance of the blue score would be 4. Suppose somehow we know this. Is it an artificial statement? Yes, but this is useful for concept building. Okay, so we are saying this many times that I somehow know the standard deviation of the population. So if we make that assumption, then we can proceed further. If we cannot make that assumption, then we need additional machinery. So suppose you are able to make that assumption. Now the sample mean for the blue scores is 81 by 9, which is 9. Now it follows that under the assumption that the values are independent, a 95% confidence interval for mu is 9 minus 9 is x bar, 9 minus 1.96 into 2 by 3. What is 2 by 3? 2 is the standard deviation because variance was 4. And what is 3? No, sorry. One sec. Variance is 4. So standard deviation sigma is 2. And population size is 9. So root n is 3. So 9 minus 1.96 into 2 by 3 and 9 plus 1.96 into 2 by 3. This gives me the interval 7.6 and 10.31. So with probability 90.95, the population mean, that is the blue score for the whole population, has to lie between 7.6 and 10.31. So if the machine translation system, the Bhattacharyya system which a company has developed, could be tested on the whole corpus, okay, the blue score must lie between 7.6 and 10.31 based on the sample that I have collected. Okay, and based on the observation, 9 samples and knowledge obtained somehow that variance is 4, we reach the 95% confidence interval as 7.69 and 10.31. What is the implication of this? Qualitatively, if the maker of the Bhattacharyya system says that I can ensure a blue score of 15, we cannot trust him now. Okay, we cannot trust him now because we have taken 9 blue scores, and the 9 blue scores are sort of pointing to a 95% confidence interval of 7.39 and 10.31. Okay, so blue score of 15, no, I cannot trust the company right now based on the experiment that I have done. Okay, he may be trustable in future when I take more samples and the picture begins to change slowly, but right now, no, I cannot accept. Okay, and if the maker says I assure blue score of 10 on the whole population, I can trust, again based on the data that I have, based on the sample that I have collected. Okay, so many times, so this is very, very logical, very scientific statistical inference. Many times we do unreasonable inferencing. Okay, unreasonable inferencing here would be that I say that I tell the Bhattacharyya the company that I just don't believe that you will have a blue score of 15. That is a strong statement, not based on data, but based on my bias. Okay, the based on data means that based on the sample size, and based on the knowledge of the standard deviation that prevails for the population, I can take this stand. Okay, so right now, if a decision maker, right now, if the organization I work for says that can I buy this Konkani Hindi machine translation system? Okay, because the maker, the company is saying I can assure a blue score of 15, which is not bad. I will advise my organization not right now. If you're prepared to tolerate a blue score of 10, you can buy. But if you really are desperate for 15 blue score, don't buy it now. Okay, I want to collect more data, and then I'll tell you. So this is data science. Okay, this is data science. I am trusting the data and making use of the property of data. But never buy from this company would be unreasonable and biased advice or conclusion, not grounded on data, but grounded on many other parameters. So let's summarize now. We are able to see that we can make useful conclusions, and you can do useful inferencing based on data, the sample, and our interest ultimately lies in the behavior of the population. And their tremendous help comes from central limit theorem, moment generating function, properties of standard normal distribution. Okay, so that was the main point to be made through today's lecture. Okay, are there any questions? Am I audible still?
Yes, sir.
Yes. So no question for now. Okay. Okay, so do remember all these observations, and of course the recording will be available, and we have taken a very useful step towards our understanding of things. Okay then, see you. Thank you. We'll meet after 2 weeks.
Thank you, sir.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you. Thank you.